Mr. Sams?
What are you doing clear over there?
Well, you know, what did you do this morning?
What are you talking about?
My
Got
word.
up, came to work.
No, I'm thinking before you went to work, there's an odor about you.
Well, usually, yeah. But
Well,
what's more offensive today than usual?
you must have put that cologne on when you shaved, but of course you didn't shave. So what are you doing with that stink?
Well, we were talking. I knew we were talking
gosh.
about vapor pressure,
Oh,
volatile
mercy.
liquids today. So I thought I'd,
Yeah, lather it on.
dress the occasion.
Tears are coming to my
wife
eyes.
sells
It's so
Avon
strong.
now. I mean,
Well,
come
it's
on, we got
Avon,
stuff
so
all
that
over
makes
the
it
house.
better.
Yeah,
Oh, have
it's
mercy!
everywhere.
It stinks so bad. Have mercy. Huh. All right, I'll try and bear it. I will try and bear it
You'll be
here.
all right.
Oh my gosh! You see,
It's got to be better than I normally smell.
what does that smell like?
I don't know.
I don't want to even
Mr.
go there.
Sam's BO.
Oh, mercy. All right, today we want to talk about vapor pressure of solutions. If you remember back previously, we did talk about vapor pressure, but that was vapor pressure of a pure substance. Mm-hmm. This is the vapor pressure of a pure solution. Here's an interesting experiment. If you had a beaker filled with water and a beaker filled with some solution, okay, an interesting thing would happen as time progresses, and then you seal it with some kind of a big jar, as you can see in this picture here. What would actually happen, it would be intriguing, is that over time the water would all evaporate and it would fill beaker number 2. And beaker number 1 would be empty. Now, why is that?
It has to do with vapor pressure.
You see, because the vapor pressure of water has a particular number at a particular temperature.
Mm-hmm.
But the vapor pressure of the solution is what?
It's always lower than the pure water.
Lower. So that means that the water will evaporate more quickly, more readily than will the solution, the salt water or whatever it might be. And therefore, what's going to happen as this evaporates and then it recondenses over here, it will do that. Very little of the actually when the salt water, assume this is salt water, when the aqueous solution evaporates, the only thing that actually evaporates is the water. The salt stays behind.
Yep.
So it actually is going to move all of the water over here. So this leads us to a concept called vapor pressure of solutions. Vapor pressure of solutions are always lower than the vapor pressure of the pure solvent.
Yeah, by the way, that showed up on the AP test a few years ago, didn't it?
It was a very exact question. Yeah. Why did that
Why did that
occur?
happen?
All right. So we said this already, but solutions have a
Solutions have a lower vapor pressure than the pure
lower
solvent.
vapor pressure than the pure solid. This is called Raoult's law. Raoult. I love his name, Raoult.
Raoult.
I say it with deep voice because it
Raoult.
sounds so good.
That's kind of weird.
That was weird. Okay, assume that a solute has no vapor pressure. By the way, in Raoult's law, if we assume that the solute has no vapor pressure, the Raoult's law is
Times.
so the pressure of the solution is equal to the mole fraction. Remember the mole fraction from last time of the solvent. Now it's a solvent.
Right.
Times
That's the thing exerting
the vapor pressure of
the solvent. The normal vapor pressure, P0.
sometimes we call that P0.
There. Yep.
All right, and we'll do some math. Now, if they both have a vapor pressure, usually this is a liquid-liquid solution, then the pressure or the equation is. So if I have a liquid-liquid, you'll say P total is equal to X of A, chemical A, times the P of A plus X of B times the P of B, etc. If you've got 3 of them, you could say XC and PC, etc. And so these are the equations. We'll use these in some mathematical examples in just a minute. Now this actually is a derivation of the phase diagram we talked about recently, is that if we have pure water right here, you can see here, this is his vapor pressure line right here, right? Mm-hmm. And this is this is a liquid and this is a gas. And what happens is the vapor pressure gets lowered because of this, and actually changes its freezing point and its boiling point, which we'll talk about a little bit later. But it lowers it. You see the blue line right here is lower than the red line, and therefore the vapor pressure is lowered. Okay? So let's do some examples.
All right.
Mathematical. Okay. What's the vapor pressure of a solution that contains 155 grams of table sugar dissolved in 100 grams of water? Well, we have to find the mole fraction is what we need to do. Now, it's important. We need to find the mole fraction of what?
Both the solute and the.
Actually,
well,
just-
in this one we just want the
Just the
solvent,
water, because
yeah.
this is sugar, and sugar will not evaporate. And so I want to find the moles of each. So for sugar, I have 155 grams of sugar. I'll say sug. And then they will see, is it 342?
342. How did you know that?
342
Holy cow.
grams of sugar. I just memorize these things.
Good grief.
1 mole of sugar. And about a half.
0.45.
0.45 moles of sugar. Now the water, we have 100 grams of water, so 100 grams over 1. There are 18 grams in 1 mole, so that's quite a few.
5.56.
5.56. So the mole fraction of the water, very important, is of the water, of the solvent, will be 5.56 divided by 5.56 plus 0.45. And that'll be 0.9, I'm sorry.
0.924.
So now that's just the mole fraction. This is X of water, right? So now I'm going to say the P total will be equal to the mole fraction, 0.924, times the vapor pressure, which they gave us to in the problem was 23.76 torr. And we just get a number 22 or something.
21.95. So let's figure it out. 22.0.
Call that 22.
Yep.
22.0 torr. Now it's lower, isn't it? Now, just as a side note, 23.7 drops to 22.0. Not a big drop.
Right, because
But a
it's
little
still
bit.
mostly water. It's 92% water still.
Yeah, so but that's how you do these problems. Okay, it gets a little bit more complex if we have two chemicals that both have vapor pressure, and so we have acetone and we have chloroform mixed together. So we know things about the acetone. We have 5.81 grams, and actually the math is very easy on this. If you have 5.81 grams, I'm going to try and convert to moles. Then there's 58.1 grams
that was
in 1
nice of
mole.
them.
This would be a 0.1 moles, right?
Yep.
Now this is of the acetone. So let's do the other one. We have the chloroform. We have 11.9 grams over 1, and there's 119.4 grams in 1 mole.
Yep. Also a.
This would also a 0.1 mole solution. So the mole fraction of the acetone, I'll call it ACE maybe, will be 0.1 over 0.1 plus 0.1, which of course is 0.2. I can do that without a calculator. That's 0.5.
I already put my calculator down.
Yep.
This is all monkey math.
And the
This is
mole
great.
math of chloroform, Cl or whatever we're going to call it, I would say
Clo.
would also be 0.5, right? Because it's the same thing.
Yep.
Now, so the P total will be the mole fraction of the acetone, which is 0.5, times the vapor pressure of the acetone. Now, which one is the acetone?
Acetone is 345. Not that it matters because they have the same
Yeah,
fraction.
that's true. But
in this problem. Yeah.
normally that would matter. So yeah, we'll write that. Then this will be 0.5 times 293. It's kind of like an average of the two, sort of. But
Yeah, it is in this case.
yeah,
319.
319. So that's simple. You just do it that way. Okay? Not terribly hard, is that question, was it?
Nope.
All right.
This is going to be a short lesson.
I
This is
think
great.
so. We've got some cool demos, though.
Woo! Yeah,
All right. Hey, colligative properties. What's a colligative property? There's a funny word.
Yeah.
Colligative! It's a colligative property.
Nice radio voice. That was pretty good.
Hey, I've got the radio voice. Can I sell you a car? Sorry,
It's
guys.
kind of scary.
Yeah, very scary. I don't want to
Drink
sell you
your
a car.
pink solution.
All right, pink solution.
Maybe
All right,
that's the
tell me
problem.
about colligative properties.
The colligative properties is when you dissolve something into a solvent, it changes the properties of that solvent. It changes the boiling point. It changes the freezing point. Changes something called osmotic pressure.
I think the key thing is it's where something, it doesn't matter what is dissolved.
Right.
So I just want to write this. Doesn't matter what is dissolved,
Just depends on how much of it.
just the concentration.
Yep.
And actually, typically, well, not always. I say typically, typically, most of the times we're going to work with molality units here.
Yeah, I'm pretty sure all the calculations have molality.
But not with
Including-
osmotic pressure. That's molarity.
Oh, yeah.
Yeah. All right. So, actually, what I want to do is we want to illustrate this with a demo. We're going to go with a demo for you in a minute, okay? Okay, guys, I'm here with some boiling water and some salt, ice cream salt. Ooh, I like ice cream. And we have, as you can see on the screen, the temperatures of the boiling water are roughly the same. These, what are they at, Mr. Sanders?
93.4, 92.9. They're within half a degree.
First of all, just as a side note, for those of you who are watching out in internet land, we live at 8,500 feet. And why is the water boiling at 92 degrees?
Because we have a lower atmospheric pressure up here.
There's a lower atmospheric pressure. So if you were to do the same experiment in at sea level, you would be seeing roughly 100 degrees in both cases. Okay? And so what I'm going to do is this is beaker number 1, and this is beaker number 2. Into beaker number 2, I'm going to make a solution. It's just water, and the solution will just be salt water. So I'm going to add some salt to beaker number 2. Notice that the water is not boiling anymore. But as I stir it, what you should be seeing also on the screen is the temperature changing. Is that correct, Mr. Sam?
It's going back up to where it was, 93.3.
Yeah, at first it drops. Actually, interesting thing, you know the reason the temperature drops?
The salt is cold.
Well, not only is the salt cold, as it's actually endothermic as it dissolves, if I'm not mistaken. The delta H1 from that, the heat of solution is endothermic, so it drops it. But I can see it starting to dissolve, and as it dissolves, what you should eventually, it eventually starts to boil. It should start to now boil at a temperature higher than the other one.
We're up to 94.6 right now.
94, and you cannot get water to boil at 94 degrees at 8,500 feet.
Nope.
However, you can if we make a solution.
95.
It should be continuing to rise as the salt continues to dissolve. Actually, I could add some more. It might dip for a moment again.
Dip.
As I add more salt, of course, because that whole endothermic thing. But we can, the more concentrated or the more salt I add, the higher the boiling point. Notice actually if you look at the beaker, it kind of stopped boiling for a moment. And now it's starting to boil again. And if you're watching the temperature gauge as on the screen, which you should, which you have no choice, is that the boiling point should now be even higher than it was before. It might take a minute or so.
Yeah, we're up to 97.2 now.
97, so we're almost actually the boiling point of water at sea level. But notice that this one over here is continuing to boil at 92 degrees.
Yep, 92, 93, sitting right around there.
In that kind of a range. And so what we could say that the boiling point of a solution is what?
It's higher.
Higher than the boiling point of a solvent. Well, I'm back again, and now instead of having boiling water, I have just some ice. And so if you look at the temperatures, they are roughly around 0 degrees. What are they at?
We got 0.6 for temperature 2 and 2.3 for temperature 1.
This is beaker 1, and it just probably needs to cool down a little bit more, and we need to have some ice melt. So, and then we have beaker number 2. So they're roughly.
Oh, there we go. Now they're both right around 0.5-ish.
Yeah. So they're about 0 degrees, which would you expect? The water is, or the ice is melting, so the temperature should be roughly around 0 degrees. But I'm going to now add some salt to beaker number 2, and we're going to observe what happens to the temperature. That's probably more than we need. Now, what you should be seeing is the salt is lowering the freezing point of the ice.
Not yet. It's still there. Oh, there we go. Now we're below 0.
You should get, if we add enough, it really gets pretty significant. Let's add some more. It has to take some stirring.
Yeah.
And that's what we're doing right here.
Down to -2.
So, and if I do this right, I think I can get it to about -10 if we work hard. But that, I think you can illustrate the point here, is that this is now at a temperature lower than 0, and it's a liquid. This is also a liquid. It's freezing, and it's roughly 0 degrees. So, what can we say about a solution? This is pure water. This is a solution of salt water. The solution of salt water has a lower freezing point than does pure water. This is a colligative property called freezing point depression. Okay? So now let's fill our paper in. The more concentrated a solution, the
higher the boiling point.
Higher the boiling point. We just saw that illustrated on the video. And the more concentrated the solution, the
lower.
The lower the freezing point.
Alright guys, I've got a bottle of club soda here, and club soda is simply carbon dioxide dissolved in water. Now it's a very, very saturated solution, probably a super saturated solution in there, meaning there's a whole bunch of CO2 in there. So as a result, since we have so much of CO2 dissolved in there, the freezing point of the club soda is much, much lower than that of pure water. Pure water is 0 degrees Celsius. This is probably -8, maybe even up to -10 degrees Celsius for its freezing point. So I have the club soda sitting in a bath here of ice water, and the ice water has some salt on it. So the water in my beaker here is melting at a temperature much, much lower than the normal freezing point of 0 degrees Celsius. It's probably, again, like I said, around -7 to -10. So it's extremely cold. It's lower than the normal freezing point of water. So what I'm going to do is in just a couple minutes, when this gets a little bit colder, I'm going to take it out of the solution, and I'm going to take off the cap, and we're going to see what happens.
That's going to be really cool. What do you think is going to happen, Mr. Sam?
What do I think is going to happen? Well, I know what's going to happen, but I want them to think about what's going to happen.
What we want you guys to think about is that if you have a solution that becomes less concentrated, what happens to the freezing point? So pause the video right now, and I want you to make a prediction.
Okay, so as you can see, our temperature of our water is about -10, -10.4 it is now. Okay, so that's pretty cold, and it's been sitting in here about 10 minutes now. So I'm hopefully this is cold enough to make this happen. Now, notice that the club soda is not yet frozen. Okay, it's in the bottle. It's still liquid. It's not frozen because we have a very highly concentrated solution. So the freezing point is very, very low, much lower than normal water would be. So I'm going to take it out. I'm going to open it up, and we're going to see what happens here. Watch it.
That is so cool, Mr. Sams.
What's happening?
I believe that is no longer a liquid.
Right.
It is now a...
It's starting to freeze itself just by simply taking the cap off of the bottle. So you can see there's ice forming here. Okay. Now bubbles are coming out of the solution. When I took off the cap, the CO2 came out of solution, or undissolved, if you will. So we have a less concentrated solution. So the freezing point of that solution is no longer really, 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 really low. It's now coming back up closer and closer to 0 degrees Celsius. Now, when it was sitting in here, that's -10 degree water. So my club soda was -10 degrees. By letting the CO2 come out of the solution, I brought the freezing point above the temperature of the water, which was at -10 degrees. So the freezing point is now above -10, closer now to 0, which is why the club soda froze inside the bottle, because it's a less concentrated solution
Just
now.
by opening the bottle, you froze it.
Yep.
But the reason you did that is, or the reason it worked, I should say, is because the freezing point was raised because it became less concentrated. So it's kind of the opposite. It's still freezing point depression, but we raised it, the freezing point, by doing that. What are you doing now, Mr. Sims?
Playing with the slush.
Playing with the icy, slushy stuff. So he's got the slush he's pulling out of there. Probably freezing his fingers. That's all right. He kind of smells bad anyways. Okay. Thanks a bunch. All right. Okay. All right. Now there's some equations. So not only are we interested, Mr. Sams, in that it's lower.
We want to know how much.
How much?
Lower.
We love math.
Quantitative.
So here's your equation here. Delta T equals I kf times m. Or delta T equals I kb times m. That kind of looks weird.
A big space there.
I know. It should be I k sub b times m. And this is delta T equals I kf times m. Yeah, I just kind of got scrunched or spread.
I have a feeling I'm going to need a textbook here to look up some numbers.
Yeah, so what is delta T? Delta T means the change in the property. Change in the temperature of the property. But in terms of the boiling point of the freezing point, it isn't the actual temperature, it's the change in the temperature. I is called, now in fancily, it's called the Van Oft factor.
Van Oft factor.
H-O-F-T, I'm pretty sure, factor. I like to also think of it as just the ionization factor. Kf is the freezing point, depression, it's a big word here. Are you depressed because you smell today, Mr. Sanders?
Not really, no.
You're okay with that?
I'm
Okay.
perfectly content with my body odor.
Okay. The freezing point depression constant, Kb, is the boiling point, I'll abbreviate, boiling point depression constant.
Not depression.
Boiling point elevation constant. Thank you.
Yes.
And M, and it's a cursive M, is the molality.
Molality.
The molality. All right. So, all right.
Okay.
So that's just make sure you understand what each variable means. Now, KF and KB are numbers that you look up on a table.
Yeah, and they're
Molality
different.
we've learned about.
Yeah, the K values are different for different solvents.
Right. Water has a
Normally you'll be
number.
using water.
Benzene has a number. They're all different. Now, I is the ionization factor
Yeah.
constant. Actually, let's do a little thing about I. All right, let's talk about this I for a second. I is the ionization factor. So if it depends on how many things it dissolves into. So if I have salt, sodium chloride, if you recall, it is a Nakalnoso, so it completely dissolves into sodiums and chlorides. I here would be equal to 2. If I've got, say, magnesium fluoride, MgF2, that breaks apart into Mg2 positive plus 2 fluorides. Here I is equal to
3. 1 magnesium and 2 fluorides.
right, so 1 plus 2. Now if I have, say,
Actually soluble?
C6H12O6 sugar, if I dissolve that in water, it breaks apart into C6H12O6 aqueous. So it dissolves. Sugar dissolves in water,
Yes.
but it does not dissociate.
No.
Here, I is equal to
1.
1. So it's important to understand. You just have to break it apart.
Yeah.
And figure out.
Covalent compounds, I is always going to be 1.
Yeah, that's
water.
important though. Covalent I equals 1. And actually there's an issue with these I's we'll talk about later. Okay, so here is that table that Mr. Sams was referring to.
Yeah.
The freezing point. So for water, the boiling point of water, 100 degrees Celsius. They're of course assuming you live at sea level. The KB, the freezing point depression constant, 0.51. Units on that are degrees Celsius per times kilogram over moles. And then the freezing point is 1.86. And then for different solvents, carbon tetrachloride, chloroform, benzene, etc., the values are different numbers.
Yeah.
So depending on the question, we'll use this table here. So we'll do an example.
do one.
So if I've got 15.3 grams of sodium chloride dissolved into 20 grams of water, what's the boiling point? Now, what we need to do is first of all find the molality. All right, so what's the molality of this equation? Actually, let's back up for a second. You can use the equation delta T sub B equals I KB times M. And I want to find M first. That's the equation, the key equation.
All right.
So I have 15.3 grams over
58.5. Oh, sorry.
over 0.2. It's per kilogram, right? So
Yeah.
actually, let me just over 0.020 kilograms of water. Remember, it's per kilogram of solvent, not solution.
Yep.
And there are 58.5 grams, this is NaCl, I'm going to write that out, of NaCl in 1 mole of NaCl. This is my molality then. So when we do the math on that, Mr. Sams, what do we get?
13
Wow.
molal. That's really concentrated.
13 molal. Okay, now an important, so that's our molality. That's this number right here. So I'm going to say delta TB is equal to, now I. Now, I. We just did this. Salt was an example I went over just a minute. It breaks apart into 1 sodium and 1 chloride. So I is equal to 2, right?
Yep.
Times the KB, now we go back to our table, was 0.51. And the molality was 13 molal. So 13 times 26, and half of that, about 13?
13.26.
13.3 degrees Celsius. So that's our answer, right?
Nope.
What do you mean?
Because it says, what is the boiling point?
Oh, yeah. When it's asking for the boiling point, that's actually the change in the boiling point. Water normally boils
At 100.
at 100 degrees Celsius. So you will, in its boiling point
So
elevation,
it always goes up.
always goes up. You add 13.3 would be 113.3 degrees Celsius for the
There
answer.
you go.
Now, in Woodland Park, water boils at 92. We saw that
Right.
just a minute ago. It would
So-
be 13 degrees above that.
Right, so 92 plus 13.3, whatever it is.
Yeah, you see? All right. Now let's do our
Wait,
next example.
It did ask for freezing. Do we want to do freezing too?
Oh, if we want to do freezing point. Oh, okay, yeah. So let's do freezing point. You're going to use the equation. All right. So to do this for freezing point, you'll do delta TF, the freezing point, equals IKF times the molality. You're just going to plug in a number 2 times the KF now. What was the KF number?
1.86.
1.86 degrees Celsius per molal times, what was it, 13?
13, yeah.
13 molal. So 26 times 2. Big number.
Yeah, 48.36. That's huge.
Yeah, most of the times that's degrees Celsius. Now, this is not the answer.
No.
Since it's freezing point depression, we'll take the regular freezing point of water, which is 0 degrees Celsius, minus 48.36.
Minus, because that always goes down.
And your temperature is just negative 48, probably sig figs degrees Celsius.
All right.
Okay? That would be very, very cold. My guess is that would be an oversaturated solution. But, oh well, that's good enough. All right, let's do another one. A solution is prepared by dissolving 18 grams of glucose in 150 grams of water. And then we get a bunch of numbers. It says what?
Calculate the molar mass
Molar
of glucose.
mass.
Oh, this is a classic.
This is such an important question.
Oh, this is great.
Star this in your notes. I have seen this.
This is like why you do chemistry, is so you can determine things molar mass.
Yes.
You can do it so many different ways.
This is very, very important because I have seen this on the AP test probably every other year. It is such an important thing to do. All right, so what's molar mass?
Molar mass is grams per mole.
So if we want to find the molar mass, you find the grams.
Hey, look, we already are
And
given
the
the grams.
Guess what? We have, now the chemical we care about is this
Glucose.
This glucose stuff is 18 grams. So this number up here is 18 grams. So I need to find the moles.
Yes.
And so I have a bunch of freezing point depression data. Is it freezing or boiling point?
Boiling.
Point. They can do either way. So boiling point. So it boils at 100.34 degrees Celsius.
Okay.
So we're going to use this equation, delta TB equals IKB times M. Because if you think about M has moles in it. It's moles per kilogram. But if I could somehow get the moles out of this equation, I'd be a happy camper.
And I think we probably can.
And
Let's
I know
put
we
some
can.
numbers in.
All right, so delta TB, all right, is 0.34 degrees Celsius.
Yep.
Now, everybody understand where I got that? Is the 0.34, it's 100.34, so the boiling point's a little higher, right? 100.34.
Yep.
And I know that I have an I. Now, it is glucose.
Yep, that is a molecular compound, covalent compound, so that I value is 1.
So this will be equal to 1. And actually, just as a side note, on the AP exam, they always have I equal to 1 in a molar mass problem. I've never seen it the reverse, because we'll talk about that in a second. KB, wasn't it 0.51?
0.51, yeah.
I can solve for the molality, right?
You can.
Times M. So if you just divide both sides by 0.51, what do you get, Mr. Sims?
0.666.
So you get a 0.67. And now watch how I do this. I'll say moles of glucose, we'll call it GL, per 1 kilogram of water. Now what I care about is I care about the moles of glucose.
Right.
But I don't have 1 kilogram of water.
No.
If we go back to the problem, we find we have 150 grams of the water. So if now watch what I do. I'll take 0.150 kilograms. I've just, in my head, converted grams to kilograms over 1. And this is the water. The kilograms of water cancel, and what do we get, Mr. Sams?
0.1005.
0.1005 moles of glucose. Now remember, molar mass is grams per mole. Now our grams from our problem was
18.
Divided by 0.1005 moles. About 180, I can do that in my head.
Yep.
The molar mass is equal to, I'm right up here, I need a space answer over here, 180 grams per mole.
And let me check that with what it should be.
I think that's correct.
Yeah, so it'd be 6 times 12.
It is 180. I've got it memorized.
Plus 12, really?
I do.
Okay.
I'm correct, I promise I know these things. It's in my head.
Oops.
Okay.
Hey, look. No.
It's 180. All right. Moving on. There's also a concept called osmotic pressure. Osmotic. Have you heard of osmosis?
Osmosis, yeah.
You know, when I was a kid and I was
there,
trying
it's
to
180.
It's 180.
I got it.
I knew that, Mr. Sams. I told you and you just didn't believe me.
I believed you. I just wanted to.
Osmotic. Osmosis is when. Well, what does that mean? What is osmosis?
Well,
You're the biology guy.
Yeah. It's when you have water crossing a semi-permeable membrane.
Is that what it is?
Yeah.
I don't think that's the official definition of it, is it? So, it's the flow of a solvent.
And in biology application, that solvent is always water. Mr. Bergman's giving me heck for...
What does semi-permeable mean?
It means only allows some things to go through.
Okay. Osmotic pressure, though, a little different.
Right.
It's the pressure exerted by, so P stands for pressure there,
Mhm.
exerted by the solution.
Right.
And a semi-permeable membrane, you already said that. What was that again, Mr. Sams?
It's a membrane that only allows specific things to pass through it. In our case, it's going to allow the solvent to go through, but not the solutes.
It's best to look at a picture through THROUGH.
Thrug.
Sorry. All right. And so actually, let's skip that and let's talk about this. We'll go to this one. If we have osmotic pressure, and so this substance here has a high concentration, so it's darker, and this one has a low concentration. And so what's going to happen is they flow from the, actually it's really it flows from high concentration to low concentration, but it's high concentration of solvent. And so the solvent will travel from the light blue to the dark blue.
Yeah, the solvent tries to dilute the concentrated one to make them equal.
Yeah. And notice something interesting here is that this blue line is at this level and this blue line is at this level. So it's a higher level. And we can actually measure how tall this layer is, and we can determine mathematics with it.
Yep.
The equation actually is a very simple equation. We'll go back here. It's the pi-mart equation.
Pi-mart.
Pi-mart. It's like Kmart, but pi. Pi-I. Pi-I-mart. So pi...
Imagine a store that just sold pie. Oh.
Isn't there pie stores?
I don't know.
I don't know.
Bakery?
I'm not
guess
a... Are you
that's
like
probably
pie?
I love pie.
I'm a cake guy. Not
Yeah,
a
I like
pie
cake
guy.
too, but man,
Cake is
pie.
better than pie.
Oh.
Oh well. But a pie, of course,
You know
is...
how weird I am?
Yes.
You know what I learned?
You
You
smell.
know what I learned when I lived in California?
I don't even know. I don't know.
Piece of apple pie with a slice of cheddar cheese melted on the top. It is the most glorious thing in the world.
Cheese and apple pie.
Yeah,
I've
there's this
not
place
tried
called
that.
Polly's Pies right down the street from where I used to live. And oh my goodness, it was amazing.
Okay. Healthy living at its best.
Oh, so
okay.
good.
Now
It
pie...
has apples in it. Apples are fruit. Fruit is healthy.
I'm not going there. All right. Pi is not a symbol for 3.1415926. Pi is a symbol that represents osmotic pressure. And it's actually the capital.
It's like big pie, yeah.
Capital pi. So
big
scientists.
pie.
So this is the osmotic pressure. I is the ionization or Van factor. M is the molarity. capital
Molarity,
M.
not molality, molarity.
Now R is important, is that it's the gas constant, but here you typically want to use 0.0821
And that's going to give you your pressure
in
your,
atmospheres.
In atmospheres.
If you use other numbers, you'll get other pressures, but
Right.
usually that. And the temperature has to be in Kelvin.
Kelvin.
Now, we're not going to spend too much time doing the math of this. I've never seen it on the AP
Plug and
test.
chug. That's
But
all
you
it
can
is.
just plug it in and chug it away. Now, yeah, we've already seen that. One cool application to osmotic pressure or osmosis is that you can actually, I don't know if you know anybody who has dialysis, kidney dialysis. If you've got kidneys that don't work, essentially what they do is they take your impure blood and they hook you up to this machine, a dialysis machine. And they pump pressure through your blood, and what happens is it gets rid of the bad stuff. The bad stuff flows through this, and then you get your purified blood. Basically, it's a fake kidney that sits on a doctor's machine deal. It's very, very cool, and of course, it's saved many lives until they can probably get a new kidney or whatever the issue is with your kidney.
Yep.
Yeah, I had a friend who had this, and he had these huge veins. They had to pull the veins in his arm out of his arm, so to speak, so they were very close to the surface because he'd sit at this, like, I think once a week, once every other week. He'd have to go to the dialysis machine and get dialysized or whatever.
Wow.
Yeah, it was not a cool deal. Another cool application is this right here. This picture is a picture of a desalination plant. Basically what they do is they pump salt water in from somewhere, the ocean or ground wells in this particular picture. They then go through and they use this pressure, and then they actually apply osmotic pressure. So if we go back to our picture, what they'll do is if this is the regular osmotic pressure, what they'll do, this is the salt water right here.
Shove it in the other direction.
They actually push the pressure down, they shove it in the other direction, and what comes out this way is just pure water. H2O. And this is what this plant does. And of course what's left over is a whole bunch of salt, or better known as brine. The brine gets pumped out, and here's your fresh water that you can drink. Actually, many boats, ocean-going boats, basically have small desalination plants, and they're all based upon the principle of osmotic pressure, and that's how they get they take pure water out of the salt water.
Yep.
My father actually owned a boat. He had this 50-foot boat he lived on for about 3 years, and instead of a house, he had a boat. And they had a lot of the boats of that size. They would have these big desalination, not big, It was probably the size of a cooler, you put your sodas in. All right, one last thing in Unit 11, or Chapter 11, I should say. It's called the Van-Off factor. We've talked about what it is, but there's something kind of weird about the Van-Off factor.
Yeah.
You expect I for salt. We said salt for sodium chloride is actually 2, right?
We would expect it to be.
We would expect it to be 2. Turns out it's actually 1.9.
Yeah.
And magnesium chloride, we said it would be 3.
Yep.
And actually it's 2.7.
Yeah.
Magnesium sulfate is 2, and we'd expect it, and it's actually 1.3.
Yeah.
Glucose is 1, and it's 1. Actually,
Yeah.
this is the only one that kind of... So the Van-Off factor, we say it's about this. So for ionic compounds, we have an interesting... So the big question is why? The issue has to do with ion pairing. When we write the sodium chloride, for example, NaCl, we assume it breaks out in 100% into sodiums and chlorides.
Yeah.
Well, it turns out occasionally a sodium is going to meet a chloride, and well, guess what? They got this opposite charges.
Yeah.
And hose, they like each other, and they get connected.
Yep.
And guess what? That counts as just like 1 instead of 2.
Yep.
And so the average, if you look at the table here, was 1.9. So a few of them pair up.
Yeah.
So ion pairing. All right? And that happens to some extent with all of the different ones. Next interesting thing to note, the ones that tend to have more positive charges, like magnesium and sulfate,
They have more pairing.
positive 2 and negative 2, there's more pairing because, of course, they're more attractive because they have higher charges.
Yeah.
And this, by the way, assumes that you have a 0.05 molar solution. If it's more concentrated, this becomes more pronounced. The 1.9 becomes 1.8. So it's very difficult to actually calculate the boiling point or the freezing point exactly. You just can give a range, really, is the best way to do it.
But for covalent compounds with the I value of 1, it's always just going to be 1.
All right, let's do one last example mathematical here. And this is using the Pi-Mart equation. Okay. It's also a molar mass equation. So what's the molar mass? We said molar mass is grams per mole. Guess what?
Hey, look, they give us grams.
They gave us grams. Now, grams is a very small number here. But osmotic pressures, we can measure them in very, very small quantities. So we know that. And to get the moles, we'll use the Pi-Mart equation.
Yes.
Now, it is a protein. And so proteins are covalent compounds. So we
Yes.
can assume that I is equal to 1. So we can say pi equals IMRT. Well, what's pi? They gave it to us. 1.12 torr.
I don't like torr.
Yeah, let's convert that to ATMs.
Let's.
Divide that by 760. And you get
1.47 times 10 to the negative 3.
and that's the pi is equal to I, which is 1, times the molarity, that's what we're going to solve, times 0.08208, times the temperature. We're at 25 Celsius, so Kelvin, that'd be 298 K. So what would be our molarity, Mr. Sams?
Molarity 6.01 times 10 to the negative 5.
6.01 times 10 to the negative 5, and that's moles per liter. Now I want just the moles, so I just need to multiply by the liters. Now our volume was 1 milliliter, or 0.001 liters, right? Over 1. The liters cancel, and I get 6.01 times 10 to the minus 8th, right?
Yep.
So we're going to take our grams. Now our grams was 10 to the minus 3rd. So the molar mass will be 1 times 10 to the minus 3rd mole, or grams, divided by 6.01 times 10 to the minus 8 moles. You're going to get a very large number here.
643.
Yeah, 16,600.
Yep.
Now, that's a huge number.
Yeah, it's protein, though. Proteins have enormous molar masses.
Yeah, so this is something that has a big, big molar mass. But if you don't understand biochemistry, you probably don't. But that seems like a huge number for a molar mass. But for a protein, that's
about standard.
About standard.
Yep.
So you can find molar mass, grams divided by moles. So it's not terribly difficult, folks, to figure out how to do this.
Yep.
So with that said, Mr. Sams, with when I'm eating cake, I usually like to eat cake with milk.
Yeah, you know what goes really well with pie?
Oh, pie.
A big cup of coffee.
Pie and coffee.
Oh.
See, maybe that's why I don't like pie, because I don't like coffee.
Maybe.
So maybe there's a
I
correlation.
do like cake with
milk. That
milk,
would be
though.
interesting. We should ask that. Would be like a poll. We should ask a poll. Do you guys know? Is pie and coffee drinkers the same? And then people who like cake, they don't like coffee? It'd be interesting to know that. I don't know.
Let's do a cell phone text poll.
Text poll.
Coming on the next podcast. Cell phone text poll. Do you like pie or coffee or cake or milk or some combination thereof?
Yeah, we could write the test.
Yeah.
We'll see you. Bye.